Alright, so we want to show that okay, so I feel like the phrasing of this exercise would be better if they introduced the, the word countable. So, a set is countable if it can be arranged in a sequence. So what that means is we basically want to show that if we look at the collection of all rectangles with rational endpoints, then this collection of rectangles is itself a countable set. Okay, so to prove this, if A and B are countable, I'll write it like this. Then so is A cross B. We can prove this by writing the elements as follows. Okay, so if we have A, and we assume that A is countable, that means that it can be arranged in a sequence. So we'll take a particular sequence and we'll label the elements in that sequence. We'll say A1, A2, A3, A4, A5, etc. And if we have the elements of B, B is a countable set, so we can arrange them in a sequence. So we'll label them B1, B2, B3, B4, B5, etc. And then, so we have this grid. Oh man, if only there was a horizontal line anywhere on this page that I could use instead of having to draw my own. Anyways, so we have this grid, and we can sort of make this sort of matrix here, where we create elements of A cross B as such. So we take the A from the row and the B from the column. So A2, B1, A2, B2, A3, B1, A3, B2. So here we've got A1, B3, A2, B3, A3, B3. Okay, and then I'm going to stop here because I don't have time for this. Okay, so then we can sort of weave through these just like we did in with the rational numbers. So you can start here, you can go down, then you can go up, then you can go over, you can go down, then you can go down again, and then you can go up, you can go up again, and then you can go down. Oh wait, no, I guess you'd go here next, and then you'd go down here, and then you'd come back here. And then you just keep weaving through here as such. And when you do this process, you end up being able to weave through all of the elements of A cross B. Because any element of A cross B is going to be AI, comma, Bj for some index I and j, and so it will be somewhere in this picture, and so you'll get to it eventually. And so you have A cross B. So a direct product of countable sets is countable. And then you can do an induction argument to see. So basically, any property that holds in the finite case can, or any property that will hold in the pairwise case will hold in the finite case generally by induction. So if you've got A cross B, then A cross B is a countable set, and if you have a third set C, then you can consider the set A cross B crossed with the set C, and then that's going to be a cross or a direct product of countable sets, and thus it will be countable. And by doing induction, you can prove that a direct product of countably many sets. No, a direct product of finitely many countable sets will be countable. Because you just do this procedure over and over and over. Okay, so there we go. We've proven that direct products of finitely many countable sets are countable. Okay, and that's the main fact that we needed. So now what we're going to do is let R be the collection of all rectangles with rational endpoints. So this should be A1, B1 through, so these are rectangles, okay, so it goes through Bn. So we are in Rn. Okay. So these rectangles, An, Bn, where Ai and Bi are rational for all I. And of course we have Ai strictly less than Bi, so that these are actually rectangles. Each element of R can be associated with an element of Q to the power 2n. So this is, this means you take Q and you take the direct product of it with itself 2n times. And the reason that this makes sense is because if you look at this, we sort of, this association looks like this. You take A1, B1 through AN, BN, and you associate it with A1 cross B, or the element A1, B1, all the way through AN, BN. So you've got a vector of 2 times n elements, and each element is in Q. So this belongs to Q to the 2n. So there are at least as many elements in Q to the 2n as in R. So basically what I'm really trying to say here is that R is not a subset of Q to the 2n, because R consists of direct products of intervals, whereas Q is just a direct product. However, R can be associated with a subset of Q to the 2n. And Q to the 2n is countable, so R can be associated with a subset of a countable set. And so R is countable. That's what we mean by saying that they can be arranged in a sequence. Alright, so that's part A. Then part B says, if you have any set in Rn and you have any open cover, then there is a countable subcover. So it's sort of like it almost sounds like a compactness thing, but it holds for any set. And instead of going from any cover to a finite subcover, you're going from any cover to a countable subcover. And this turns out to be a property that's specific, it's more about the topology of the space rather than about the sets itself, which obviously that must be the case because it doesn't depend on the set. So let O be an open cover of A, which is some subset of Rn. And let X be an A. We want to find a finite subcover, or a countable subcover of O, and so we want to find some element in O which contains X. Oh wait, no. Okay, we'll just take it one step at a time. Then there exists some set U, and I'm going to call it UX, in O, such that X is in UX. Since UX is open, sorry, I probably shouldn't text in film. UX is open. There is a rectangle Rx such that X is in Rx, which is contained in UX. Remember, this is such rectangles exist for any open sets. Okay, so now we can shrink the endpoints of the intervals in Rx to become rational endpoints such that the resulting rectangle Sx satisfies both. Because we're shrinking to rational endpoints, Sx will be an element of R, and also we can shrink them in such a way that they still contain X. And of course, this is going to be a subset of Rx. Okay, so for example, if you take a particular index I and you've got Rx, so you'll have Ri upper and this should be Ri upper and this should be Ri lower here and here, and then this will be the xi, so that's the ith coordinate of x. Because we're on the real line here, you can choose rational numbers here and here, so we'll call this qi lower and qi upper, which are rational endpoints and which are strictly between the endpoints of the original rectangle and between such that this interval still contains the ith coordinate of x. Okay. So that's just an aside. Now for each, so these Sx's, they have countable. These Sx's are taken from the countable set R, and so that's what we really need. However, we now need to go back to this open cover O. So for each Sx, choose some Vx in O such that Sx is contained in Vx. And why is that possible? Well, that's possible because we have one already. You could just choose Ux if you wanted to. Because Ux is an example of such a set. Because Ux, it contains X. And it also contains Sx, and Sx is contained in Rx, and Rx is contained in Ux. Alright, so we have this. And, oh, I guess, does this, okay, are we using countable choice here? I don't really care. But yeah. Alright, so now what we're going to do is that each Sx is in R, as I've mentioned, and R is countable, as I've mentioned. So there are countably many Vx's. Okay, so this is a little weird because X is being chosen arbitrarily from the set A, which is, it could very easily have uncountably many points. So how did we get to finitely many Vx's? So let's see here. So we started with X, then we chose an open interval or an open set Ux, which contains X. And then we chose an open rectangle Rx, and then we shrank it to an open rectangle Sx. Okay, so that's where we sort of make the important move, because there's only countably many Sx's. And so what's going to happen is that there's going to be a whole bunch of these Sx's that overlap. There will be infinitely many, there has to be uncountably many cases where you can choose different points x and y, but they'll be covered by the same rectangle Sx. So Sx will equal Sy. And this has to happen because you're choosing uncountably many points there are uncountably many points that you can choose from, but only countably many Sx's. So uncountably infinitely many of those Sx's are going to end up overlapping with each other. And so that's where the real condensation happens. And then, of course, for each Sx, you choose a particular Vx. All right. So in particular, I said that this Vx that we choose, it could be Ux. But in general, all of the Ux's could be different. And so we need to allow for some of the Vx's to overlap. Because that also needs to happen in order to get a countable collection. But we don't really know too much about how the overlaps happen or when they happen. That will depend on the specific open cover and stuff, which we never sort of study. This is all sort of done in the abstract. But we know, anyways, that there are countably many Vx's. So we simply let cursive V, which I had to go and Google how to draw because I haven't done it in years, be the collection of all Vx's such that x is in A. And so like I mentioned, A could be uncountable, so we could have uncountably many Vx's. However, since if that is the case, then most of those Vx's will overlap, and so we'll still have a countable set. Then V is a countable set, and it's every Vx is in O, so it's a countable subset of O. And we also know that for any x in A, you can find a Vx, and so V covers A as desired. Because that's what we were looking for. We were looking for the set V of, which is a countable subset of O, such that those sets all cover A. And that's what we've done. So Yeah, having a collection of so you're having this countable collection of rectangles is really important in this topological space, um, because it allows us to have a countable collection of sets which can cover any particular set. And so this ends up being related to a lot of uh, important definitions and ideas in point set topologies, specifically a set being separated. We say that a topological space is separated if it contains a countable dense set. And so, of course, the Q to the n is a countable dense subset of R to the n, and so Rn is a separable space. And there's important facts about separable spaces and the ability to have like a countable base. But that's all stuff you can read Baby Rudin, you can read Fallend if you want to learn more about that. But yeah, those are important ideas, and this is sort of leading up to that and introducing you to that. But anyways, we've done the exercise, and so we're done.